Example 2, confidence interval for estimating the population standard deviation for pulse rates. Listed below is a simple random sample of pulse rates, which is in beats per minute or BPM, obtained from adult females based on data set 1, body data, and Appendix B. We want to be able to construct a 95% confidence interval estimate of the population standard deviation. So here's the data that's given. First thing we want to do is check the requirements. Well, the sample can be treated as a simple random sample. Now what we want to do is determine, looking at the normal QQ plot. So let's take a look at that. So in StatCrunch, what I'm going to do is you can go ahead and then title this as body data and then enter each individual value here, and you can see that we end up having 22 of them. So the first thing we want to do is we want to look at the graph. So we're going to select graph, select QQ plot, and then we're going to go to body data. We're going to make sure we have the horizontal and vertical lines selected, and then select compute. So when we take a look at the graph here, we can see that this line is now graphed sort of in the middle of all these points. So we can say that this looks like a normal distribution. So the accompanying normal quantile plot that we just looked at suggests that the sample is from a normally distributed population because the points are close to a straight line pattern. Now we want to be able to draw and label the curve. And what I mean by that is, since we're going to look for the 95% confidence interval, let's go ahead and do that. So for the 95% confidence level, we're going to do the following. We first need to find the areas in that tail. So first thing is first, we want to find out what alpha is. And alpha is going to equal 1 minus 0.95, which gives us 0.05. And then number 2, we're going to take alpha and then divide that by 2. So 0.05 divided by 2 gives us 0.025. Okay, so keep in mind here that since we're dealing with the chi-square distribution, that means that we know that we're going to start here at 0. And it is a skewed right distribution. Okay, so this is the chi-square scale, which means that we're going to have a chi-square value here on the right, and then we also have a chi-square here, critical value, on the left. So the first thing we want to do is, since we know that 0.025, that's going to tell us that this area over here represents 0.025. And it tells us that this area also represents 0.025. Okay, so let's go ahead and shade that in there on the right-hand side. So on the right-hand side, this represents 0.025. So that means if we want to find the critical value for the chi-square on the right, we're going to use the area of 0.025. Now for the chi-square on the left, it's a little different. So we can see here that the shaded part to the left represents 0.025. But for the chi-square distribution, we want to find the area that's to the right of that. So we need to find the area to the right of the critical value of the left chi-square value. So in order to do that, we would then do the following. We would take 1 and then subtract what they have on the left, which is this 0.025, and that gives us 0.975. Okay, so I'm going to go ahead and highlight this. So if we want to find the critical value on the left, we need to use that area to the right. If we want to find the critical value on the right, then we're going to use that area to the right. So let's go ahead and move a little further here. So if we're using table A4, okay, we first used a sample size of n equals 22 to find the degrees of freedom, because there are 22 in our sample. and the degrees of freedom is going to be n minus 1. Well, 22 minus 1 gives us 21. And then in table A4, we're going to refer to the row corresponding to 21 degrees of freedom, and then refer to the columns with areas of 0.975 and 0.025. Okay, now for a 95% confidence level, we divided alpha, which was 0.05, equally between the two tails of the chi-square distribution, which is the reason why we get 0.975 to the left critical value, and then 0.025 to the right of the right critical value. So let's take a look at the table here. So if we take a look at the table, okay, and if we look at 0.025 and then scroll all the way down in that third to last column there and look for 21, if we scroll over here, we're going to get 35.479. That's going to be our right critical value. So let's go ahead and write that out. So we get 35.479. So this is 35.479. Now we want to find the critical value on the left using the area of 0.975. So if we come up here and look at 0.975 and then scroll all the way down to 21, we're going to get 10.283. So therefore, the critical value on the left is 10.283. And therefore, we get the following critical values. Okay, now if we wanted to use StatCrunch, then we would select Stat, Calculators, and then chi-square. So let's go ahead and do that. So we're going to go to Stat, select Calculators, and then go to chi-square. And so if we want to find the left value, we want to make sure that we have the degrees of freedom to be 21. We want to make sure that we have our inequality to be greater than or equal to, because if we want to find the chi-square on the left, we're going to put in the area to be 0.975. And if we do that, you can see that rounding it to 3 decimal places gives us 10.283. Okay, now let's hit refresh. So go to options, refresh. Again, we're going to put in the degrees of freedom to be 21. Again, we want to make sure that we use greater than or equal to. But now we're saying we want the area on the right to be 0.025. And therefore that represents, rounded 3 decimal places, 3.479. So therefore that's what we get for our critical values. Now that we have our critical values either using the table or StatCrunch, now that we have those critical values, we need to find the sample standard deviation. Okay, so in order to find the sample standard deviation and StatCrunch, we have our data already in here. So we're going to go to Stat, go to Summary Stats, and select Columns. And then from here, we're going to select the column for body data and then go to Standard Deviation. And now we're going to select Compute. And therefore, that's what we're going to get. So let's go ahead and copy that for our standard deviation. So if we round that standard deviation to 5 decimal places, we get 9.91959, which is what we get here for our standard deviation. And we know that the sample size of n is equal to 22. So now we're going to construct the 95% confidence interval by evaluating the following. So we're going to plug in our values for the formula here. So what do we know? We know that n, okay, is equal to 22. So we're going to plug in n to be 22. So there's 22, there's 22. Okay, and then we're going to plug in our standard deviation, and our standard deviation is 9.91959. So there's 9.91959 and then 9.91959 there. And then we have our critical left value, chi-square, is 10.283. And that's over here on the right side in the denominator. And then we have our critical value on the right, which is going to be here on the left side of that. And so therefore, we're going to go ahead and then put in this into our calculator. Okay, so putting in our calculator, we have parentheses 22 minus 1, close the parentheses, and then multiply it. So open other parentheses and put in standard deviation of 9.91959, close the parentheses, and then square that value, and then select enter. And then we're going to divide that by 35.479. Okay, so let's go ahead and then copy that value. Okay. And then let's do the other side. So we can just go back up here and then press enter. And that's going to be, if we press enter again, that's going to calculate that same thing that we did in the numerator on the left side. And now we're going to divide that by 10.283 and then press enter, and then it's going to give us that value. So rounding it to 4 decimal places, we get 58.2419. On the right side, we get 200.9495. So therefore, that's what we get on our calculator. Now, this is the variance. This is the population variance confidence interval. To find the population standard deviation, we need to find the square root of each part before rounding, and then rounding to 1 decimal place, which would yield this 95% confidence interval estimate of the population standard deviation. So we need to take the square root of those numbers. So if we come back up here, or if we want, we can say second square root of 58.2419. Well, that gives us 7.6. And then if we take the square root of 200.9495, well, that gives us, rounding it to 1 decimal place, 14.2. So therefore, that would give us the confidence interval for the population standard deviation. So here's the interpretation. Based on this result, we have 95% confidence that the limits of 7.6 beats per minute and 14.2 beats per minute contain the true value of the population standard deviation. The confidence interval can also be expressed as 7.6 beats per minute, 14.2 beats per minute, but it cannot be expressed in the format of S plus or minus